Hello everyone, I'm Zihao from ICT, and today I will give a talk on our recent work on the data center architecture. And my partner is preparing the demo, the FPGA demo, so near the end of the talk we will give some demos about our works. So first we go to talk about the background. Data centers suffer from a trade-off between the utilization and QoS, and according to the service conduct by McCarthy, the average utilization in data center is about 6% to 12%. So to improve the utilization, letting the application share the same infrastructure is an easy way to do this. However, sharing may cause interference among applications. Researchers in Google observed that by locating different programs in the same physical servers, they may suffer from interference more than 3 times. There are a lot of red entry here, so that the performance degradation is more than 3 times. Okay, so in 2015. Google announced that isolating programs from each other on a shared server is a very hard problem. So they are calling for the hardware supports, new hardware supports. So what happened to the traditional hardware, and so it cannot deal with this problem. So we say that the traditional hardware is the QoS unaware. In the traditional computers, applications share the same infrastructure, here, and hardware components with shared resources such as the last level cache, and the memory controller, and the I/O bridge. So these hardware components are unable to distinguish requests from different applications. Just the figures in the right show that. So different applications from the perspective of hardware, so the hardware cannot distinguish them. So this means that the hardware is still in the state of unmanaged sharing. Here, unmanaged sharing state. So no matter how strong the isolation the software can achieve, the hardware can still cannot guarantee the QoS. Just like in the traffic system. So if we cannot distinguish the ambulance from other cars, so it's very hard to give the high priority to the ambulance. So let's talk about how to deal with this problem. So we first talk about the networking. So they use the label techniques. They have 4 features. The first is a fine-grained features. This means every packet has a label, and then they correlate the labels with the user's demand, and then the labels is propagated in the whole network. And finally, the network device will process the packets differentially based on the label. So because in the networking field there are a lot of this kind of label techniques. For example, the MPLS and the SDN. So we are asking a question: can we borrow the technique from the networking to the traditional traditional architecture to solve the management sharing problem? We observe that the computer is inherently a network, so we can observe from the behavior in the traditional hardware. And hardware components communicate via internal packets, for example, the PCIe packets, and NOC packets and QPI packets. So actually, we can view the computer as a network. So so we can borrow the label technique from the networking field to deal with this problem. So based on this observation, we propose the label the Wagner architecture we call LVNA. So similarly, it has the 4 features which is talked about just now. So to construct the LVNA starting from a traditional computer, we first add some labeled register to the request source. For example, the call, because the call will send memory requests, and another is the device, because they may start DMA requests. So we first add a label register to the call and the device. Second, we correlate each of these labels to a virtual machine. For example, different colors in the picture corresponds to a different label. Then we will do the propagation, and the memory, all the requests will attach with a label to go through the whole computer system. Okay, so you can see there are different colors of packets. And finally, we will add the software-defined label-based control logic, short of Zihao here, to all sharing resources. So by these ways, the sharing resource can distinguish requests from different applications. So based on the LVNA, we propose PART to perform the fine-grained control mechanism. So a PART is short for the programmable architecture for resolving on demand. So a PART is a proof concept of LVNA. The goal of PART is to improve the data center's utilization without too much loss of QoS. So next, we are talking about how to implement, how the PART decides to use the, how we decided the control logic to enable the PART feature. So in the control logic, we use tables. We use tables to store parameters and statistics information for the hardware components. Parameter tables store label-based rules for control logic to support differential servers for different requests. So you can see each row is correlated to DSI. This is our name to the label. So different labels will have different parameters. So the sharing resource controllers can process requests with different labels with different policy. And secondly, the statistic table is similar to this. Is similar because each row is also correlates to the label, and this is the field to statistics. So the statistic table, the behavior of the statistic table is just like per label performance counters. So we can, for example, we can achieve the per label cache miss counter by the label feature. Another advanced functionality in our design is the trigger agent mechanism. So we say the closed loop control. Yeah. A trigger is a condition referring the statistics tables. For example, here the cache miss rate and such as the cache miss rate greater than 30%. Here, the action runs in the formula to adjust the parameter table. So, for example, we can adjust the weight partition configuring when the miss rate trigger condition is satisfied. So, by these ways, we can allocate more weights to to the applications with this DSID or this label. Finally, we introduce a centralized platform resource manager to manage all control logic as well as the label registers. So here we introduce the PRM here. So PRM is just like an IPMI module. PRM will connect all of these control logic and run a linear space firmware, here. So since PRM can use all control logic as device, so we can abstract them as files. So to access the control plane from the control logic from PRM, we can simply use something like cats to query the information about the control logic or query the specific parameters. Or to setting the parameters, we use echo, something like this. So it's very convenient. So finally, we are talking about some kind of evaluation. We have implemented the part on both a full system simulator and FPGA platform. They are also open source. Actually, we have two versions of the FPGA implementation. The first version is the micro-based version. Now it is deprecated and it's replaced by the RISC-V version. So all of them can be accessed from the GitHub. So this is our final design on the Chinese VC709 evaluation board. So here there are 4 cores, and the core control plane will control them, and the label register is located in the core control plane, and also there are cache control plane and memory control plane and the I/O CPU control planes here. So all of them is connected by this control network and then connected to the PRM. So PRM can manage the control planes by the control network, and also the cores can run the linear space. So we can by the label features we can partition the whole machines into 4 sub-machines. So we call the sub-machine the logic domain here. So each logic domain can run linear simultaneously. So they are physically isolated to each other, and there are also file servers to store the image and some test bench. So they are connected to use the Ethernet. So here is some evaluation results. So by using the 4 logic domain, we run one MCF benchmark as along with 3 attackers. So without part, the MCF will suffer from performance degradation to the extent of about 48%. But with part, we can protect the MCF from the attacker. So the MCF will only have a performance degradation about 7%. Next, we are talking about how to switching the part because the first version we are implementing on microbase. So we have switched the whole implementation to RISC-V. So RISC-V will because it is open source and we can add the labels in the code easier than the microbase, and also the RISC-V will provide a better ecosystem to us. For example, it's very promising to run container on RISC-V. So, our goal is to establish the label RISC-V branch. So this graph is taken from the technical reports And this is the architecture of the rocket ship. So how do we implement the label on the rocket ship? So first, yeah, we add the label registers here. So then each memory request go out of the tail, we will attach with the label. Second, we will add the control plane to the share logic for example, the L2 cache. So with this control logic, we can achieve something like the weight partition. For example, the red part is partitions to the tail 2, The tail 1 cannot access this part. But for these parts, they are shared between two tails. And also we will add a modified bridge here to convert the tail link to, we add a new members to the tail link 2 bundles here called DSID, and we will convert this DSID to the user signal of a side protocol. So we finally we will add another control logic here, the memory control logic. So we have there are two features here, and the first is the address mapping. So we can when a request come and we can inspect its DSID and decided to map to which segments. And another is the label token package to perform the something like array limits. So finally, we will add a PRM to connect all of these control logic and label registers. For the overhead, we give some examples here. To add labels into the rocket ship, we only use 16 lines of chiplet code, so it's very convenient. And here are some details. First is add the DSID members in the bundles, in the bundle of tail link 2, and attach the labels at the tail link 2 master of the core tails. So then we will finish the label propagation to hold the whole rocket ship as well as the AXI part, the peripherals. And for the resource overhead here, we give the implementation result in the Vivado. So the green part here is about the control logic. From the data, we can see that there are less than 5% of resource overhead for the control logic. So if we switch to a more complex code, for example, boom, so this number will be even less. Okay, now we'll give two demos, and we'll first talk about what this demo should do. So the first demo is is about NoHype. The goal of NoHype is to push the software hypervisor down to the Elvina to remove some runtime overhead generated by the software hypervisor. So by this, we can isolate the resource, for example, the address space and device by the control logics, and partition into the servo submachines. For example, here, this is the whole machine without the traditional machine. So this is the machine based on Elvina. So we can physically partition the whole machine into two submachines and run different operating systems simultaneously. Because Windows is not very easy to run on FPGA, we also rerun the Linux finally. So this shows that there are two logic domains here. They both running different benchmarks simultaneously. The second demo is about the memory bandwidth control. So we will use the labels token package to isolate bandwidth attackers. For example, we have the string benchmark. If we run the this benchmark alone, we will have this bandwidth consumption. So if we running the benchmark with the attackers, so the bandwidth consumption is decreased. So by isolating the attacker using the labeled total buckets, and the bandwidth will go back to the original. So next we will show the demo. So we will switch. So the after half is the PRM. So so the bottom half is the left is the first logic domain, and the right is the second logic domain. So first we will show we can start the two logic domains simultaneously. So we will be running some scripts, and this is the image transferring. Now it's running. Yeah, actually, they report some call traits. Maybe it is something related to the debug model, but we do not use the debug model. So this call trait isn't harmful, so that we can ignore it. Yeah, maybe unpacking the RAM disk. Okay, there are some errors here. Okay, so for the sorry that the demo is failed. Okay. So my partner is going to fix this, so we will first continue. Maybe at the end of the talk we will do it again. Okay, finally, we are going to talk about what does the system stack will change if we introduce the Arena. So the first is talking about hardware. So we are going to put the label everywhere in the hardware. So actually, we have a plan to tape out So we are going to tape out 4 boot with SMT support. We also want the label to propagate into the core pipeline. For example, to manage the ROB, something like this. Okay, I think this is a very challenging project. So second, for the hypervisor layer, so we will use NoHype. NoHype is already finished. So the goal we have just talked about is to push the software hypervisor down to the Arena. So we remove the runtime overhead. For example, in the x86 for the VM entry and VM exit, we pause some cache flashing, TLB flashing, and privilege switching. So this will introduce some overhead. So by using the NoHype, the virtual machine will run directly run on the hardware, and they do not need to do this kind of operations. So next is the operating system layer. So we are going to provide fine-grained labeling, and we will add the fine-grained label as a context resource. There are 2 categories of this. The first is the process categories. The first is, for example, the process levels and the thread levels. Actually, we have already finished the process level and integrated into the C groups. And another kind is the address space related labels. For example, we we will give different labels to different functions, or even different labels to different objects. For example, we will label this array with a critical label, and do something like this. And also, we will provide some library to using these features more conveniently. For example, we may provide p-thread create with DSID or malloc with DSID, something like this. For the compiler, we will express the QS information from the source files. For example, we will run the code something like this. We will specify the time to call this function. So the programmer may want this function to finish within 10 seconds, something like this. So this kind of information will transfer into two different kinds of results. The first is the address space related label information. Maybe we will present it with the extra ELF sessions for the loader, for the operating system loader to read this kind of information and store this information in the process task structure, something like this. And another is the resource requirements. So we will generate some kind of QS description files for the scheduling framework to let them schedule the resource according to this file. And this is about the framework. And so we will expose the QS resources to the scheduling frameworks. For example, we have already integrated QS resources into the OpenStack. For example, the cache, because the traditional OpenStack cannot manage cache, so we do this. Or we will expose the maybe the I/O bandwidth to them. So there are a lot of things to explore when we introduce Alvina. Yeah, there are a lot of problems. Some of them is we have already done, and some of them we are ongoing, and some we just have an idea and we have not design and implementation, and some we will leave to the future work. So this program will cover from the theory and systems, and also the whole computer system stack. So for summarize, Alvina is a model of the software-defined architecture, and PAR is a proof of the concept of Alvina, and the label of RISC-V is an implementation of the Alvina. So this ends my talk. So we have built a WeChat group here, so you can scan the QR code to join the discussion group.
Well, thank you, Zihao. That was very interesting. It's always ambitious to throw up a live demo on the stairs beside the podium. So maybe, I don't know if you guys signed up for a demo session tonight, but you should make sure you put set it up over there, and hopefully you get it running, because it's pretty interesting. And we're behind. I'm going to shorten my talk so that we can ask a couple of questions of Zihao here, because I think there probably might be some. Any questions? Did everybody get that? Yeah.
The total number of lines of code change in Chisel was 16 for everything?
Actually, this is the part of adding the labels to it, and not including to the control logic implementation. Yeah, because the telling. Yes.